So here we have a photo of copper 2 sulfate. Now, the first thing to note is that I called it copper 2 sulfate. I didn't just say copper sulfate. Now, this was actually addressed in my previous video on when a solution is cooled down rapidly versus more slowly, and looking at crystal size. Because copper 2 sulfate is a completely different compound from copper 1 sulfate. Okay, they're both copper sulfate, so we need to specify which one we're talking about. So this is copper 2 sulfate. Now, it's actually hydrated copper 2 sulfate, or its proper name, copper 2 sulfate pentahydrate. Okay, so penta, well, that means 5, and hydrate is to do with water. Pentahydrate means that for every molecule of copper 2 sulfate, we've actually got 5 water molecules tied up in the crystal structure. So this is not just copper 2 sulfate, that's all, nothing else. We've got water molecules tied up as well. Now, what we want to do is a very simple prac and then some very simple math to prove that it is actually pentahydrate, that there are 5 water molecules tied up for every crystal of copper 2 sulfate. Because depending on the salt, you might have a monohydrate or a dihydrate or an octahydrate, decahydrate, etc. But for this particular salt, there are 5 water molecules tied up with the crystals, so it is pentahydrate. Right, let's go ahead and do a very simple prac and we shall demonstrate that. So here's a photo of a crucible and lid. Silly me, I actually didn't take a photo of it being weighed, but I did weigh the crucible with the lid, and the mass was 26.3 grams. And then I put in some copper 2 sulfate, and here we can see that. Now, I didn't actually care how much I put in. I reweighed it. So here we go. This is the crucible lid plus the copper 2 sulfate. So we've got 32.1 grams now. So, you know, I put in a few grams of the copper sulfate, but I didn't actually measure out, I want to put in 3 exactly or 2.5. It's a moot point. It doesn't really matter. Okay, so at the end of this, we're going to use stoichiometry, which is essentially the math behind chemical reactions. And so how much we use isn't really important because we're going to be doing a bit of math, simple math, don't stress, and looking at a ratio. So it's the ratio that's important, not the actual mass that you had. Anywho, I've got some copper sulfate in there. I put it over the Bunsen and I heat it. So here we are doing that. Now, you note it's not sitting on a gauze mat. We're using a pipe clay triangle to heat the crucible directly. You can also see in the photo that the lid is slightly ajar. Now, what I'm actually going to do is heat it up more than 150 degrees Celsius to get rid of that water that's tied up in the crystal. We call it the water of crystallization, or sometimes the water of hydration. So I want to drive that water off, and then I'll reweigh it, and the mass should be less because I've gotten rid of some water molecules. But we need to give the water a chance to escape when we drive it off. So hence the lid is not quite on fully. And here we are, I've lifted up the lid. This is just after a few minutes of heating. It doesn't really take too long. And we can see we've still got the pretty blue color. The blue of the copper 2 sulfate is actually from the water molecules tied up. So you can see around the edges there, it's we've lost quite a lot of the blue color. Anhydrous copper 2 sulfate, that's without the water of crystallization. So we say anhydrous, or we call it copper 2 sulfate anhydrate. That's actually much more white in color. It doesn't have the pretty blue color. So we've started to drive off some water from around the edge, but not enough. We've still got lots of blue. So we need to do some more heating. So here we are, heating it some more. Now, all told, I heated it for roughly 5 minutes or so, 5 or 6 minutes. And that was really enough to get it nice and dry, to drive off the water. So here's another photo, not quite completed. I needed to heat it a little bit more because we still got some blue color. And here is a photo when I've essentially finished my heating. We don't have the blue, we just have the anhydrous copper 2 sulfate in the crucible now. So next thing to do is let it cool down. We don't put hot things on our balance. Now it's cooled down. I just left it for like another 5 or so minutes to cool down and reweighed it. And now we have a mass of 30 grams. So this is the mass of the crucible and the lid plus the anhydrous, the dry, I guess you could call it, copper 2 sulfate. Now from this we can determine the mass of water that was driven off. Okay, so from our 32.1 grams, if we subtract our 30 grams, we must have had 2.1 grams of water that has now gone away. Right? Okay, we'll get to the math in just a sec. But before we do that, let's take a look at this photo. Now, what I've done here is just put a couple of drops of water back into the crucible. So I heated it, I drove the water away and lost the pretty blue color. The reverse of that, if I put the water back in, just with a couple of drops of water, as we can see here, we get the pretty blue color back. Okay, it's in the crucible, which is fine, because we would also get the heat back, right, by using heat to drive off the water. Okay, but then when you put the water back in, you actually get the heat back. So, you don't put this stuff in your hand and then put a couple of drops of water on it, because it gets really hot really, really quickly. All right, so let's take a quick look at some simple math. Don't stress, it's a simple equation, it's not much math, and we're really just going to look at the ratio, and you'll see, it's not that bad. Here we go. Okay, so let's have a look at doing a bit of stoichiometry. Remember, that's essentially the maths behind chemical reactions. Stoichiometry can be used for various things. You might be determining what could you be finding out? The empirical formula. You might be looking at the percentage yield, maybe the percentage composition. In this case, we're trying to find out the degree of hydration, right? How many water molecules were tied up with each molecule of copper 2 sulfate. So whatever it is that you're doing with the stoichiometry, there's a general sort of process you should really be following. And it's to start with the equation, and then you'll be looking at the mass that you have, or maybe it's a number of particles, but often it'll be the mass. You'll be converting to moles, looking at a mole ratio, and then probably converting back to a different mass of a different species. So that's pretty much the process that we're going to do here. So remember, the moles is the SI unit for the amount of a substance. It's what we use in chemistry a lot. So you might be thinking, wait, the amount of stuff is the kilogram. But, well, no, it's not. That is an SI unit. So is this SI? Yes, it is. Tick. But that's actually the SI unit of mass. In fact, it's actually the only SI unit that has a prefix. So, if we're talking SI units, which is think of it as the standard international system of units, right? It's what we use throughout the world. It's the Système International de Unité, right, in French. So, in terms of distance, we have the meter. In terms of time, we've got the second. In terms of mass, we have the kilogram, right? So it's actually not the gram. It's the only SI unit with a prefix there. Anywho, in terms of amount of substance, we're talking moles. Moles is the SI unit for the amount of a substance. And the symbol for moles is the mole. Okay, so we will be looking at the number of moles, and N says the number of moles, just like D might be for distance, and that's measured in meters, and a T might be for time, measured in seconds. Well, N is the number of moles measured in mole. Okay, so here we go. Let's do the whole stoichiometry process, and we start with a chemical equation. So we've got our hydrated copper 2 sulfate. We don't actually know the degree of hydration, so let's just throw it down as an X. Good little algebra thing. Don't know a number, put in a letter. An X is always a good letter to use. Now, of course, we do know the number. It will hopefully turn out to be 5, because the answer is 5. Now, it's a pretty simple prac, so it really should turn out to be 5. But let's remember, we're pretending we don't know that it's 5. So, okay, let's try and work that out. Now, we heated this, so what we could do is write heat over the arrow. We don't have to write that, but this stuff was heated to produce this stuff. Now, what we were left with was anhydrous copper 2 sulfate, or copper 2 sulfate anhydrate. But how did we get just that? We drove off some water. How much water? Well, X amount of water molecules. Okay, hopefully it'll be 5. Let's see. Now, we weighed some stuff at the start. We had a crucible and a lid and some of the hydrated copper 2 sulfate, and that had a mass of 32.1 grams. But just before I put the salt into the crucible, I weighed just the crucible and lid, and that had a mass of 26.3 grams. So that tells me that my mass of the hydrated salt, if I just take my 26.3 away from my 32.1, that was a mass of, 5.8 grams of the hydrated salt. At the end of the prac, when I'd heated it for long enough, I reweighed. Well, I let it cool down first, and then I reweighed it, and its mass was 30 grams. So again, if I do a bit of simple math now, if I take my 30 away from my 32.1, that says that I got rid of 2.1 grams. Somehow I got rid of that. Well, I got rid of it because that was the mass of the water, was 2.1 grams. And now I can actually use these numbers to determine the mass of my copper 2 sulfate, which is really what I need. The mass of the hydrated salt, this 5.8 grams, we're only going to use this once to find out what this mass is, and then we won't be using that 5.8 grams again. So again, by a simple subtraction, I can take my 2.1 away from my 5.8 and come out with a mass of 3.7 grams of the anhydrous copper 2 sulfate. So this 5.8 grams, I don't need that anymore. These are the two masses now, the dry copper sulfate and the water. Those are the two masses that I'm going to be needing. Now, okay, so we've got our equation. Great, we have a mass, cool. And remember, the next thing was to turn it into a number of moles. So we can compare the moles of this compared to the moles of that. We can't compare masses. We can't just say, oh, look, well, the dry salt was, 3.7, and so the ratio of that to the water, well, we can't do that because all the atoms have a different relative mass. So we can't just do a straight up mass comparison. We have to look at the amount of the substance and compare that. Now I've got a nice little equation in chemistry over here. We have the moles N is equal to the mass divided by the relative mass. And the relative mass, of course, you get from a periodic table. So now we can work out that the moles, let's do the copper sulfate first, the moles of this stuff is equal to, remember the basic steps. You start with an equation. You rearrange if you need to. I don't need to. Then you put your numbers in. So I've got 3.7. Oh, that's not 7. 7. There we go. 3.7 divided by the relative. Come on, what's wrong with this? There we go. So divided by the relative mass of copper 2 sulfate. Now this I happen to know is 159.6086. That was a relative mass. Why didn't my... Something's up with my pen. I better check the battery later. My stylus, I should say. Anyway, we calculate the number of moles, and I'm not going to give all the decimal places, but roughly it's 0.023 mole of copper 2 sulfate. And then we do the same thing for the water. So the number of moles of, and actually this is another thing you could do, just put in brackets what you're talking about. So the number of moles of the H2O is equal to, of course, the mass over the relative mass, which is equal to 2.1. The relative mass of water is roughly 18. It's very, very close to 18. It's actually 18.01528, but we don't need to worry about too much great accuracy right now, and that comes down at 0.117 mole. Okay, so now we know that for every 0.023 mole of copper 2 sulfate, and that might not sound like very much, but a mole is a really, really big number, we need 0.117 moles of water. So we've actually got more moles of water than we do of our salt. But water is a smaller, less massive molecule. It's lighter. So that's why, even though we can have a greater amount of moles of it, it actually has a less total mass. Cool. Now, in stoichiometry, we look at the mole ratio. And what we have here is, just separate this all up, we have the ratio of copper 2 sulfate to water molecules. Okay, so we find that ratio. So, excuse me, we take our larger number divided by the smaller number. Okay, so we're going to do 0.117 divided by 0.023. And that will give us our, what we call the mole ratio. Okay, so hang on, where's my calculator?
reach for this, and what we've got, 0.117 divided by 0.023 equals, so the mole ratio is 5.086956522. Okay, so 5-ish, which, remember, is a number that we want. The mole ratio is one of these to 5 of those. Okay, it was slightly more than 5, but in terms of the accuracy of all this, we just want a general mole ratio with whole numbers. So now we can say that, okay, we had 1 copper sulfate for every 5 water molecules. Okay, so there's our mole ratio. We've just put it back into the equation, 1 of the salt for 5 of the water molecules. So there we go. That's our degree of hydration. For every 1 copper 2 sulfate, we needed 5 water. So now this X, we can get rid of that. In fact, we can get rid of it nice and cleanly. There we go. And we can put in our degree of hydration. So there, we came out at 5, which we knew we were going to because, well, I knew and I told you earlier. And so the name of this pretty blue stuff is copper 2 sulfate. Okay, so the copper 2, this pen, what's going on? Try that again. Copper 2 sulfate, there we go. So the copper 2 part is the first name. Remember, we could have copper 1 sulfate or copper 2 sulfate. They're different compounds. So we use Roman numerals and brackets to show which one we're talking about. And that's usually how we talk about it, copper 2 sulfate. But actually, its name is copper 2 sulfate penta for 5, because there are 5 water molecules, so pentahydrate. So next time you're using that pretty blue stuff that someone calls copper sulfate, you will actually know, well, its proper name is copper 2 sulfate pentahydrate, or hydrated copper 2 sulfate. This name that I've written here gives a little bit more information because it tells us the degree of hydration. There were 5 water molecules. So rather than just saying, yeah, it's got some water tied up in the crystal structure, we can say, well, yeah, it's got 5 water molecules tied up in the crystal structure. So there we go, copper 2 sulfate pentahydrate. That's a fairly simple prac with a little bit of maths. All good.